to our e-learning series on joint connections. This e-learning webinar is part of a series that we've been offering at CAE Associates covering a variety of topics. If you haven't had an opportunity to attend any of the e-learning seminars previously, you can go on our website at www.caeai.com. If you click on the resource or reference library list in the lower left-hand corner of the website, you'll see a list of previous e-learning seminars that we've covered, or topics. They range for over a wide variety of things, from parametric best modeling to loading to using MAPDL and Workbench. There's a whole series of topics-based presentations that might be helpful for you. So you're free to go to our website and download previous presentations, either the recordings of the WebEx seminars or the actual presentation files that were used during the demo. If you happen to be a New Jersey or New York resident, you can earn continuing education credits for attending the full webinar. We just ask that you complete a survey at the conclusion of the presentation. Today we'll be talking about joint connections. In addition to that, we'll also spend a little time discussing stiffness behavior of bodies in mechanical and how that pertains to certain boundary conditions. And then we'll basically take you through the range of joints that are available, some advantages to using spring-type joints, and basically show you how easy it is to set up and run a lot of these problems. So rather than going bullet by bullet here, we can jump right into the presentation. Well, what are joint connections, first and foremost? They're very simply put, they're kinematically admissible constraints between two bodies. So imagine you have 2 points, one on each body, and you're defining a constraint with a known degree of freedom between those 2 points. This is accomplished with an MPC 184 element, and the degree of freedom that is chosen or is used is based on the type of joint that you're using. So for instance, if you were using a translational joint, you'd have a single translational degree of freedom. Something like a revolute joint will have a single rotational degree of freedom. Now these joints can have anywhere from 1 to 6 degrees of freedom, and again, we'll go through the various types of joints that are available in the presentation. But first, let's talk about stiffness behavior of bodies. This is a relatively new capability inside ANSYS Workbench, where we are allowed to define the stiffness behavior of a particular body as either rigid or flexible. Previous to this, everything was considered to be flexible and was meshed with finite elements and all the associated degrees of freedom with that mesh. Now, if you have a situation where you have an assembly of parts, and there are certain parts of that assembly that you consider to be more rigid than others, you can define their stiffness characteristics as rigid, and it will substantially save in computational time because of the way those bodies are then represented in the solution. Essentially what's happening there is that you're looking at the bodies in mechanical. You can actually see the geometry, but once you define them as a rigid body, from a solver standpoint, they are reduced to a mass at the CG of the body, and then they're connected to either ground or to other bodies using bonded MPC constraints, or bonded MPC contact. So what you see on the left is essentially the view, the setup of the joints, everything that you would normally see in the pre-processing end on the mechanical side. When you submit that to the solver, this is what ANSYS is actually seeing. Only the flexible bodies are meshed with finite elements. And so deflection and stress and strain are all calculated for those bodies. On the rigid side, all you're getting are forces at those connection points, and that's due to the force transfer through the structure based on the types of joint connections you define. When you bring that result back into mechanical to post-process, you're back to seeing the actual bodies, the rigid bodies. You won't see any deflection or stress because they're rigid. There was nothing calculated for them. But you will see the standard result types for the flexible bodies that you have defined. When we talk about loading flexible versus rigid bodies, for flexible bodies, we've been doing this for quite a while in mechanical, we have all the traditional loads available to us, things like pressures, forces, bolt pretensions. They require a finite element mesh, and the flexible bodies will have that. When we talk about rigid bodies, once a body's stiffness behavior has been defined as rigid, the only load that is valid for that particular body is going to be what's called a joint load. So there has to be a joint predefined with a specified degree of freedom, and then we're going to apply some load with respect to that degree of freedom. In the case of a static analysis, we're typically applying either a displacement or a force load at that joint. If it happens to be a dynamic analysis, whether it is an implicit transient analysis, or if all the bodies happen to be rigid and we're using the rigid kinematics tool, we can put on loads as displacement, force, but as well as velocity and acceleration. When we talk about constraints for flexible and rigid bodies, once again, flexible bodies, we're pretty familiar with the constraints that we have available to us. We're fixing degrees of freedom on the funded element mesh, so fixed supports, frictionless supports, compression-only supports, all valid for flexible bodies. Rigid bodies, again, though, cannot have any of these types of loads or supports applied to them. They are limited to basically a joint condition that is going to constrain them either to ground or to another body. So if you try to put something like a frictionless support on a rigid body, you're going to get an error in your details menu, and the solution you'll get an error pop up when you try to solve, and you'll have to correct that because it's not valid for that body. Now, mechanical has a variety of different types of joints that you can use, from fixed, as I mentioned, to revolute. Essentially what you're doing, you have anywhere from 1 to 6 degrees of freedom. In the case of fixed, obviously you have 0 degrees of freedom. And you are selecting the active degrees of freedom for that joint based on the type of joint that you select and based on the reference coordinate system. So we're going to align a reference coordinate system such that we have, say, a translational constraint in the appropriate direction. If you review the ANSYS help, bring this up here, there's a section on joints. If you just search on joints in ANSYS Mechanical, you'll see that there's a nice explanation of the different types of joints and a nice little graphic to give you an idea of what we're talking about here. So here they're talking about the constrained degrees of freedom. For the revolute joint, they're leaving out ROTZ, and you can see essentially what you're making there is a hinge. We look at the cylindrical joint, similar, but it also has an axial translational degree of freedom in that particular situation. Again, some other translationals. There's the slot joint, which is kind of an interesting little animation there. The universal joint has ROTX and ROTZ degrees of freedom. The spherical joint is an interesting one. I imagine what it would take to get this type of problem to solve using a traditional surface-to-surface contact. There'd be a significant amount of iteration going on there. But here, when you're using a joint, you're specifying what those degrees of freedom are. You're assuming that you know how this connection is going to react, and it ends up being a much more computationally effective way of doing that than using a traditional contact pair. A couple more in here. There's a bushing joint, and then new at 14.5, you scroll down to the bottom, you'll see this point-on-curve joint, which looks like a little bit of a roller coaster here. Essentially, this joint has 1 degree of freedom, and that degree of freedom is the XY coordinate along the path that defines the joint's range of motion. So essentially you have, in this case, a curve. It figures out where essentially it is on that curve, and that XY coordinate then becomes the degree of freedom setting for that joint. So kind of an interesting way to put an arbitrary range of motion or direction of motion on your joint features. Now to our PowerPoint presentation. One other one that I wanted to point out to you is the spring joint. Spring joints become very useful in situations where you need to apply a preload, but you have large deformation in the system. If you use a traditional bolt preload in Workbench, where you have a meshed bolt and you're applying that preload, that is a small deformation assumption, because the bolt preload actually uses constraint equations to apply that preload initially. The direction of that preload is never updated with respect to large deformation when you're using a standard bolt preload. One of the nice things about the MPC representations, in this case the spring joint, is that the direction of that preload will be updated as the structure deforms. So this is a nice way to get around situations where you've got large deformation and you need to put that bolt load in there. Let me show you now from a demo standpoint how easy it is to set up this type of spring joint. So I'll just pop up an example problem here. You can see we have 2 flexible plates that are being put together. They would typically have something like a fastener between them, whether it's a bolt or a rivet or something else. But in this case, we don't want to have to physically model the rivet for a number of reasons. One, it's more degrees of freedom in the system. And 2, we're pretty sure this thing is going to see some large deflection because it's a fairly flexible structure. And we want to make sure that our bolt preload is updating with respect to deformation of the part. So in this case, I'm just going to suppress my bolt body, and we'll go through the steps for defining this joint connection. Now, the joint connections essentially use a surface-based constraint. So there's a couple different ways we can define this. The easiest way is to simply go into the connections region and specify that we're going to put in a body-to-body spring connection. Now, you'll see there's a couple of pieces of information that we need to apply here in the details menu. We'll start out with the stiffness. That would be the stiffness, the axial stiffness of the bolt. So I'm just going to say it's roughly that. If we're doing a dynamic analysis, you can also put in a damping coefficient for that spring. In this case, we don't need that. We're doing static response. Now we need to scope the geometry. So we have a reference and a mobile setting for any joint that we define in a body-to-body scenario. So what we'll do is start out by specifying the reference on the top of the plate. Assume that we have, say, a washer along with our fastener here, and we want to distribute the preload along that face. We can simply select that face, and then we specify what the connection behavior is going to be, whether it's going to be a rigid or a deformable type of connection. In most cases, the bolt and the washer head are pretty stiff, so we're going to leave that as rigid. And what that is doing is essentially defining a rigid connection to that surface to an average location at the center of the bolt. So we'll flip this thing over now. We'll go down to the mobile end, and we'll pick the bottom face, or the bottom annulus, representing the washer on the underside. Click on that, and you can see we get a little representation of our joint there, and it knows where to place the actual joint or the spring because it's taking the average location between the two reference geometries. So that was kind of an easy way to do this. It was a fairly simple geometry, but what if it wasn't obvious as to where we wanted that spring to be located? What if we needed to offset that in some way? Well, another way that we can do this, let me suppress this joint right here, is we can use remote points. So we can define remote points first and use those to connect the joints. And the remote points can either be located by XYZ coordinate, or you could align them with a coordinate system itself. So let's say I have a coordinate system on the top here, a coordinate system on the bottom. I can use those two coordinate systems to then define remote points. So I've got a remote point here on the bottom that is, again, rigidly, in this case, connected to that face, but located at the coordinate system. So we specify in the details what the reference coordinate system is. In this case, my coordinate system is bottom, and my XYZ offset for that, which, by the way, these offsets can be parametric, is 0, 0, 0. So I'm placing it right at the center. So I've got a remote point on the top, I've got a remote point on the bottom. The definition of the remote point is where I specify the connection behavior, the rigid or deformable connection. So if I do this with remote points, I never have to worry about doing it when I define the joint. And again, you do this in situations where it's not obvious that ANSYS can decide where to place that particular spring. Like in this case, it's fairly obvious, but there may be situations where it is not so. So now we can simply come down back to our connections region here and put in a body-to-body spring. Okay? And then rather than scoping to geometry, we will pull this menu down and scope to a remote point, and then we'll just pick the remote points from our list. So there's my remote point on the top. Scroll down, do the same thing over here, remote point, bottom. So you can see I've got, we can see represented in here the reference coordinate systems of the remote points, as well as the spring position and orientation for the model. Again, pretty easy to set up and use. Notice also that your bolt pretension can be parametric. So if you need to use the parameter set to do a sensitivity study on that bolt pretension, that is fully available as well. And again, the main crux here is that the advantages are there's no need to mesh, model and mesh the bolt, and the preload direction is going to be updated. In fact, if you look at my figure here, you can actually see the axis of that spring that is moving. Because it is an MBC-based joint, it is going to be updated for large deformation situations. I had another question on Tuesday when we did this presentation as to, well, how would I account for the added mass of the fasteners? Well, you could simply do that with a localized mass. You could also locate the mass of the bolt at each remote point to account for any additional mass due to the fasteners. Okay, so let's talk about defining joints now. I'm going to bring up another example problem here. we have a plier geometry where I've defined the upper two bodies, or the upper three bodies, as rigid. You can see in sort of the darker gray color. And then the lower two, the lower jaw and the lower grip, are going to be flexible. So these lower two bodies will be meshed with finite elements. We can do things like use a surface-to-surface contact region between that flexible body and also the rigid body. The rigid body in this case would be the target surface for that contact region. So that's possible between flexible and rigid bodies to do the nonlinear contact. As far as the joint connectors are concerned, we can put them in manually. So let's start out, say on the end here with the very end of the wrench. Let's say we're going to fix it at that end. We simply go down to the connections region. In this case, we could insert a connections group so that we have them all in one organized place. We'll change our connection type from contact to joint, and now I can simply go in and start adding in various connections as I need them. Click on that. We'll specify that we're going to use a body to ground fixed, and we've essentially fixed the end of that rigid body. As I mentioned before, if this is a rigid body and you try to put on a flexible type of constraint on there, something like a frictionless support, it's not going to allow you to do that. It shows the geometry selection in yellow because you're not able to, that face doesn't physically exist in the solution, and it will not be able to accommodate that support. So you're going to need to correct that, find another way to constrain it with a joint condition before you generate the solution. Okay, so we have a joint now that we defined manually on the end there. Another way that we can define joints, again, we can manually define body to body or body to ground joints, as I've already shown. But the connections tool, when we specify that our connection type is joint for a particular folder, also will allow us to automatically create those joint connections for the selected bodies. Out because I try that again. So we'll put in a new connection group, insert connection group, specify that our connection group in this case is not contact but joints. We would scope to various bodies. In this case, we'll just use all bodies in the system. And when we right click and create automatic connections, it's going to create a series of joints based on the various bodies that we have identified or scoped this particular joint connection folder to. So I'm going to go back now and add in that rigid one as well. So we'll pick on that face on the end there. Body to ground fixed. And now we just need to treat these very much like we would the setup of a traditional contact scenario. We're going to go joint by joint, evaluate it, and see if it's what we need. Now, in this case, I've got two rigid bodies highlighted on the top. They're currently fixed together, so that's going to act like a welded connection between those two bodies. I'm going to keep that one. That one's a good one. Come down to here. Well, I've already got a contact region defined between these two bodies, so I don't need that joint. I'm going to delete that like I would unneeded contact region. Now I'm going to start to define connections at these pins between the various components in the part. So you can see, much like contact, the affected bodies in a particular joint region are highlighted or shaded as opposed to transparent. So in this case, we have a joint that's initially defined between the lower jaw and the upper part of the housing. We just need to tell it the type of joint we want to use. So start right up at the top here. This is going to be a revolute joint because we're going to represent a rotational degree of freedom about the pin. So we'll change that to revolute. And now we need to identify the mobile and the reference bodies. So we'll start out just by picking some geometry here. And again, this can be done either by picking, it can be done with name selections. If you have name selections coming from your CAD tool, this is a quick and effective way to do this. But we're going to say that in this case, our reference geometry is going to be that cylindrical post. And then our coordinate system is going to be at the center of that post. So if you look up in the upper left here, you can see the active degrees of freedom for this joint. The only one active for a revolute joint is rotation about Z. Rotation about Z in this case is normal to the axis, or is parallel to the axis of the pin, which is what I want. Now we need to go and define the mobile geometry. The mobile geometry will be one of the faces on the lower jaw. So let's continue that process through the remaining revolute joints here. And we start by setting that to revolute. We specify the reference geometry. We align the coordinate system with the geometry so that the Z is in the right direction. And then we pick on the mobile geometry to finish off the process. Again, just for the sake of being repetitive, set this again to revolute. And you'll see in a moment while I'm doing this, we'll be able to actually preview how these joints react using what's called the configure tool. Side of the interface, that's our reference. Okay, so I've got a bunch of joints defined. I've got this part fixed on the end. I've got a contact region is going to need to be, because it's nonlinear, is going to need to be determined iteratively during the solution. But if I want to check the validity of my joint connections right at this point, I can do it if I'm using a session of ANSYS that has solver capabilities. If it's a post situation, you're not going to have this capability, what we call the configure tool. But if you're using any license that supports solving, you'll be able to do this on the fly. And simply all you do is you pick one of those joints, pick on the configure tool up in the toolbar, and then you'll see that only the active degree of freedom for that particular joint is highlighted. So if I click on this and I start to move it, I can see if my joints are being connected correctly. Well, my entire mechanism should move, so that's telling me I'm missing something up at the end of this link. So right off the bat, before I've even generated a solution, I'm able to check and see if I've got everything fully defined. So we need to go back and add another connection to the end of this link. So let's revert that back to its original position. Let's come up here to, again, to our joints region. We will pick on, say, this edge right here. And we can insert a body to ground revolute. Again, we want the coordinate system, or the local coordinate system, to be along the axis about which we want to revolve. If we need to change that for any particular reason, it's very easy to do. You simply pick on the particular axis that you want to move and pick on the position that you'd like to move it towards. That's just as simple as that. So pick on one and rotate it over if you have to. So our local Z is the blue axis. That's going to be the axis about which we're rotating. We've got that particular joint set up there. Let's go back and check our configuration again. So we'll pick on one of those revolute joints, go to configure. Now we can see that the entire mechanism is responding. So quick and easy way for you to determine, like I said, before you even generate a solution. This is actually using the solver to figure out the instantaneous position of the parts in this assembly. Okay? It's treating everything as rigid and just doing a kinematics analysis as I adjust this joint setting. Now this configure tool can be used, as I said, to check your various your connections, make sure they're all valid. You can also use it to set the initial position of the geometry. So let's say I wanted to open up the wrench and solve it in that position. I can set that to be the actual position, or I can always revert it back to its original location. So you can use that to very quickly and easily figure out how to set those conditions. I'm going to show you one more capability with joints here, what we call stops and locks. So let's take our revolute joint here on the link and suppress that for the time being. And let's basically add in another joint there. Let's add in a translational joint. So in this case, we'll pick again on that edge right there. And we'll go body to ground. We'll make it translational. Now in this case, the X degree of freedom is the only active degree of freedom. And what I want basically the local X to be in the direction that local Z is currently in. So here's a situation where I would say, okay, X is now going to be in this direction. That's going to be the positive direction for it. So I reorient that so that my translational direction is the way I want it to be. And so again, we could check that configuration once again. We could use the configure tool. We can grab right on that translational degree of freedom, make sure that's all making sense. That looks good. But now, in addition to this, let's say we were going to model a situation where there might be a gap between the set screw on the end of this plier and that link, because that link basically has to pivot on the end of the set screw in order for the jaw to be able to close. So down on the bottom here, in the lower left-hand corner of the details menu, you'll see that we have a stops section, and you can specify for the degree of freedom a minimum and a maximum type of stop, and that stop can either be a stop or what's called a lock. Now, in the case of a stop, we're simply defining the limit of that motion. So let's say that this link can only go back, or can only go forward in this case with respect to that axis, 0.1 inches. We can specify a minimum. Again, up here on the top, we'll specify this also as a stop, and we'll specify that that can only go backwards, say 0.05 inches. It's got to be a minus value, 0.05 inches. So I'm defining a range of motion for this particular joint. Now, when we configure that, we should see that it's only going to allow us, it only lets me pull it as far as the particular stop ranges that I've specified. You're basically limiting the range of motion of that joint to account for some kind of gap or slop in the situation. And we have two different types of stops we can use. The stop just simply says, all right, don't go any further than that, but if I reverse the load, that particular joint is allowed to, there's no resistance to it moving back along the way it came. If you change that to a lock type of stop, once you've hit that limit, it'll actually lock the joint at that location for the remainder of the analysis. And that may be something that you need to do depending on your particular scenario. One other important note with these stops and locks is that you have to have large deformation turned on during the solution in order for these to be valid. If you don't turn on large deformation, you will see that the stops and the locks are ignored during the solution. So just keep that one in mind. It's noted in the documentation, but it's not always obvious. Okay, so a couple other things I'd like to show you. We've used the configure tool to check our basic degrees of freedom, make sure that everything's connected correctly. If you wanted to take a less graphical, say a more formal approach to that, let me unsuppress my Revolute, suppress my translational. What you could do is go up to the connections region, under joints here, and turn on the worksheet. Click on your show preferences, and there's something called the joint DOF Checker. So we can basically display joint information, we can display the DOF of the joint. If we have any contact regions in there, we can look at a connection matrix which shows both joints and contacts. We click on generate here, and it basically gives us a nice summary of our setup. The joint DOF checker essentially figures out how many bodies you have, assumes that each one of those bodies has potentially 6 rigid degrees of freedom, 3 translations and 3 rotations, and then based on the joints that you've specified, subtracts out the degrees of freedom that you've constrained. So you can see down when we get to the bottom here, we basically over-constrained because I have that extra constraint in there, the translation and the Revolute. Normally you'd like to see that you have some free degrees of freedom when you generate the solution. A little bit further down here, we have the connection matrix itself. It basically gives you the parts across the top versus the parts in the column, and kind of shows you in a matrix way exactly how the parts are connected together. That's something fairly new. I think at 14 they introduced that, but again, that's another way to check and make sure that all of your connections are accurately defined. All right. So let's talk now about post-processing of our joint connections. When we're doing any kind of a result evaluation for the joints, what we're going to be using is the probe tool. If you right-click and insert under the probe, you'll see there's an option for looking at joint results and spring results. And essentially what we're getting here are the forces that are being transmitted at those joints or springs. So let's pick on the joint here. We're then prompted to specify the joint at which we'd like to look at that result. So we see our available joints in this pull down. So let's just pick on, say, that Revolute joint there, and then we simply evaluate the result to get the force distribution. And you can see that's also going to be done on, in this case I have a nonlinear analysis with multiple load steps. So you'll see all of the results over the solution history. So a quick and easy way to check your results. We'll also do things like it'll give you a net vector of the total load, so basically the SRSS of that load, and the associated vector is shown here.